Alright, hey guys, so this is Ms. Medina, and in this video I want to show you the central limit theorem. And what the central limit theorem says is that regardless of the shape of your population distribution, and my population distribution right now has this weird shaped distribution, it's called the Weibull distribution, and regardless of the fact that my population distribution looks like this, if I were to go out there and take samples and average those results and plot those results, and that means make a sampling distribution, the sampling distribution or the distribution of the means is going to be normal, and that'll happen regardless of what the original population distribution looked like. So for example, I can start with the Weibull distribution, or I can start with a log normal distribution, and it will look like this. It's log on a log scale. Or I can have a skewed distribution, and I could sample this distribution, and when I plot the means of my samples, it would actually be normal. It would be normal around over here, and I'm going to prove this to you by through this video. So let's start with the Weibull distribution, and this one has 500 groups. What is this one used for? This one can be used for particle size, atmospheric particles. It works perfectly for it because for the smaller sizes you have tons and tons of atmospheric particles, so you have lots and lots of them. But for the larger particles, the size, the amount of them starts decreasing, because the larger the particle size, it would fall out of the atmosphere. Alright, so let's say that I have lots of these particles, but I can't measure all of them. So what I'm going to do is I'm going to go out there and I'm going to take one sample, one measurement only. And right here, one sample, reset, and it's just random, so it's going to pick any of these. So here we go. The computer has picked a value over here, and if you can see, it's blue. And one value it's plotted, and that's not enough for me to make any assumption on this population. So I'm going to go ahead and do it again. Click start again, and now it picked a number here. And as you can see, this is the statistics. These are the parameters for the yellow distribution, the original population. And the mean is 0.98. I've made two measurements. This is for my sample distribution. I've made two measurements, and the mean is 0.58 or 0.59. As you can see, I'm completely way off, but I've only taken two samples. I'm going to do this 50 times. I'm going to go out there a third time, fourth time. Every single time I'm making a random measurement. Fifth time, 6, 7, 8, 9, and as I make the measurements, you can see that they're appearing on the screen and they're calculating them. This over here is not going to change because that's for the yellow. The yellow is set. That's the population. This is for the sampling that I'm doing right here. Now the mean is 0.69. So I'm going to do this 50 times, so just bear with me. 10. I'm up to 20. 31. 46. 40, 50. I've made 50 measurements, and I've plotted them all, and I get a mean of 0.86, and my standard deviation is even higher than my mean. So this is just horrible. It doesn't look like anything, but the reason for it is because I've only sampled, the sample size that I was making was 1. Now, what if I were to go out there and instead of doing only one measurement, let's say that I did 2 measurements, and I averaged them out, and then I plotted them. So let's go ahead and try that. My sample size is going to be 2, and I'm going to plot this. So I'm going to go out there, make 2 measurements, average them out, and plot them, and I got 0.83. Do it again, go out there, make 2 measurements, see right here, and it's still doing 1. Oh, we're not supposed to click set. I apologize for that. It should work now. Sample size is 2. And there you go, it picked 2 numbers and it averaged them out, divided by 2, and it got 2.106, and it plotted it for me. I'm going to go out there and make 2 more measurements, and make these 2 measurements, 0.174, 2.658, divided by 2, and it got 1.416, and it plotted it. And I'm going to do this every single time. I'm going out there, I'm making 2 measurements, I'm averaging it out, and I'm plotting the average. This is my sampling distribution. As you can see, only these numbers are changing because these are the numbers that correspond to my samples. And I'm going to do this 50 times. and I'm up to 40, and I did this 50 times, and I'm really tired of going out there and making measurements. Now it still looks all over the place. The mean that I got this time was 0.96, which kind of is close to 0.98, but the standard deviation is 0.85, and that's just horrible. And you can see that there the blue is all over the place. Right? So this is now good. So a sample size of 2, it improves what it looks like, but it's still not good enough. So I'm gonna change the sample. I'm gonna go out there and I'm gonna make 5 measurements, and I'm gonna get the average of those measurements, and I'm gonna plot them, and I'm gonna do that 50 times. So I'm going out there. You can see right here in this box I made 5 measurements. I divided by 5 to get the average. I got 1.796, and I'm plotting 1.796. I'm going to go out there again, make another 5 measurements randomly chosen, divide by 5, 0.313. And I'm going to do this, my sample size is 5 now, and I'm going to do this 50 times, 50 trials. And I'm plotting it all, and as you can see, it's less spread out than before. Oh, and I went all the way up to 59. Well, that's fine, 59. The mean is supposed to be 0.98, and I got 0.89, but my standard deviation actually went down. Now it's 0.41, and you can tell that because before we had measurements all the way over here. So it's still spread out. Does it look normal? Not completely. It's got some weird funky shape. It's trying to look normal. Let's change the sample size to 10. Sorry about that, pressed the wrong button. 10, I'm going to set it, and now what I'm doing is I'm going out there and I'm getting 10 measurements, and I'm dividing by 10 to get the average, and I'm plotting the average. So I'm going to plot the average of all of these means, and I'm going to do this 50 times, and I promise not to go over 50 this time. You see, be patient, you're going to see it. 50 trials. The mean that I got for the blue, the sample means, my sampling distribution is 0.90, which is close to 0.98, but look at my standard deviation, it's 0.25. And now it's starting to look just a little bit more like a normal distribution. Why? Because as I'm increasing the sample size, my averages are getting better, they're getting closer to the mean. By the way, the red here is the mean, the 0.98, and as you can see, it's not quite on the red. So I'm going to increase my sample size to 20. And I'm going to go out there and I'm going to make 20 measurements, and I'm going to get the average of those measurements. See, 20 measurements right here, and get the average, and I'm going to plot these averages, and I'm going to do this 50 times. And as you can see, going up to 50, it's starting to look more normal. The average is close, 0.98, 1.02, and my standard deviation is now only 0.21. And this is what the central limit theorem says, that regardless of the shape of the original population, in this case it was a Weibull distribution, when you go out there and you sample the population and you average it out and you plot those means, the distribution of the means, of the sampling distribution, is going to be normally distributed. I'm going to go out there and I'm going to make 35 measurements, average them out. These are the 35 measurements. I'm averaging, dividing by 35, and I'm plotting them. And I'm going to do that 50 times. And what's happening to the sampling distribution? The sampling distribution is taking on the shape of a normal distribution. And this is only 50 trials. You know, you can do 100 trials, you can do 200 trials. Let's say I sample 50 and I average them out. See, let's hope that stuck there, 50. So I picked 50 values, divided by 50, and I get an average, and I plot it. The larger my sample size, the more it starts looking like a normal distribution. And that's only when I do 50 trials. Now let me show you what happens here when I just let this go. Let me close this out. Let's say when my sample, no, stop. When my sample size was 1, set, and I'm just going to let this sample. And look at the trials right here. It's just, we're up to 100 trials, up to almost 200 trials, and it's all over the place. And it's just plotting, it's just randomly sampling the distribution. It doesn't really look like much, okay? going to stop this. I'm going to increase the sample size to 2. Okay? And I'm just going to let it rip. There we go. And it's just sampling away. It's getting 2 numbers, averaging them out, and then plotting them on the scale. Now it's, yeah, normal. Maybe a little. And it's got weird outliers. Over here we have outliers, sort of. And our standard deviation is 0.65, which is very significant. Now let's say that I increase the sample size to 5, and let's just sample. Now the mean is 0.98, 0.93, 94. The standard deviation is 0.45, and it's starting to look more normal. See? Let's keep on increasing that sample size. Let's pick 10. Let's set it, and let's start all over again. So now what it's doing is picking 10, and it's doing way more than 50 trials. It's 10, averaging them out and plotting them, and you can already tell that it's looking more and more normal. Look what happened to the mean. It's 0.96, supposed to be 0.98, it's 0.96, and look at the standard deviation, it's only 0.28, and you can tell it's spread out, but not as spread out as before. You don't have all the outliers over here, okay? But it's still broad. 0.28 is kind of a large standard deviation. All right, let's see. Let's increase the sample size to 20. Okay, set and start. So now this is going out there and it's sampling 20, and it's dividing by 10. And just look at the simulation. You see how it's just starting to look a lot more normal. The average, the mean is 0.99. It's supposed to be 0.98. And look at the standard deviation. Now it's only 0.21. It's less spread out from the mean. And it's just looking more and more normal. And you can see that it's getting taller and taller because most of the measurements are about the mean. And this red line represents the mean. If I increase my sample size to 50, you know, for the purposes of this class, you should know 35. At 35 is when you say that your sample size is big enough in order to say that it'll have normal distributions. Look at this. The average is already 0.98. It's supposed to be 0.98. And look at the standard deviation, 0.15. It's just, I mean, the deviation has just gone down. That means that it's staying very close to the mean. Alright. So this is what the central limit theorem says, that if you have a population, regardless of the shape of your original population, in this case is Weibull, if you sample that population and you have a large sample size, larger than 35, and you plot the averages of all of those measurements, if you get this sampling distribution right here, it's going to have a normal shape. Alright, we did this in class, and I just wanted to reiterate it. So after you're done watching this video, make sure that you answer the questions on the other link on the form, the Google form, and then click submit on Edmodo. Alright, you guys have a good night.